Lecture 5.7, Capacitors in Parallel and Series Combination. We now assume that all capacitances of capacitors have been computed. So it doesn't matter whether we talk about a parallel plate capacitor, a spherical or cylindrical, they all have the same behavior. So all capacitors have the same characteristics. And what we mean by that is that if I look at capacitance, there is this material, right? The dielectric material. Times the geometry of the setup here. Now, what's going to be really important here is that when we write out circuits, circuit is not a material thing, it's a geometry thing. So what I'm saying here is that we're going to ignore this, and we're going to say here is that circuits is only about geometry. There is no material aspect in circuits other than we know that there's a dielectric, yeah, they have a permittivity, but that's all we care about. We don't care about anything else. So the easiest capacitor is the parallel plate capacitor. Since the parallel plate capacitor is the easiest to work with, this is our go-to capacitor. So in other words, when I look at the capacitance of a parallel plate from now on, it's just C, and the only thing we care about is the geometry. And the geometry of a parallel plate capacitor is very clear. It's about the plate area. It's about the plate separation. And you can see here that this is directly proportional to the area and inversely proportional to the plate separation. So now we ask an important question. What combinations of parallel / series capacitors change one area or two plate separation? Because this is geometry of circuits here, we look at the combinations of series and parallel to actually answer this question. And here's what we know. If we increase area, that means that tells us that elements are added in parallel. So putting things in parallel increases area. The same thing happens with what happens if you increase plate separation. That means when you do that, elements are added in series. So now my job here is set. What do I want to do? I want to show you sketches that tell you specifically about this. So let's start with capacitors in parallel. So if I look at capacitors in parallel, what I'm going to need is that I'm going to need a reference capacitor. So let's draw this. So here we have a reference capacitor. And when I label this, what that really means is that I'm going to set up a nice thick line. Nope. Nope. Let's trying to figure out how to actually do this. How about I'm going to set a thick line here, and I'm going to say that this guy right here is my top plate. This guy right here is going to be my thick line at the bottom. And then, of course, we have a dielectric in here. That might be too big, but let's just go with it. So this is my capacitor. And I'm going to call this capacitor C1. So now, what I'm looking at is that I'm going to look at the current. So I'm going to bring this down a little bit more. And I'm going to say that I'm going to look at what does the current see when it's coming to the upper plate. So now, if I add things in parallel, so adding in parallel effectively increases area. So what does that mean? Well, it means this. So now let's think about three capacitors in parallel. So then I'm going to say, here's going to be, I'm afraid of running out of space, so I'm going to only draw 1, 2, 3. And then I'm going to come in and I'm going to draw my plate here like this. And of course, I have my dielectric in here. So if I put them in parallel, then that means I have to have an equipotential that connects all of these guys right here. And of course, I do the exact same thing down below. So let's follow the current. So the current comes in here. And what we see with the current is that it must split. Why must it split here? Because I have a junction here. So what happens to the current? Part of the current goes in this direction, part of it goes here, and part of it goes there. And so when I'm looking at these capacitors, what is actually happening? Well, what we're seeing here is that because it's splitting like this, we see that the current sees 3 plates, and that automatically increases the area because now I have 3 plates. So when I look at this thing, the effective circuit now looks like this. So I tried to draw each of the orange lines as one square. So now look what I'm going to do. I've now effectively increased it by 3. That's what the charge is then going to see, the current. So if I'm looking at my capacitor, I now see that I have a wire, and the effective factor is that it now sees a bigger area. That's what the current is seeing. So if I try to write this out, we then say that this here is what we now call the capacitance for a parallel combination. So right here, this is an effective model of capacitors in parallel. So let's redraw this now. So if I redraw this thing, what does it really say here? It says this. So one can replace 3 capacitors in parallel with a single equivalent parallel capacitance. In other words, if I have capacitors, so if I think about my capacitors, I imagine that I have a capacitor here, another capacitor here, and another capacitor here. And each of these is 1, 2, 3. And so when I look at this thing, I see here that I have this combination right here. I can replace this with a single capacitor, which is now C parallel. That's the equivalent capacitance here. Now the question is that, how can I replace that? How can I replace this with one equivalent capacitance? The reason why we can replace multiple capacitors in parallel is due to geometry. And this here, we see here is that capacitance, which is proportional to area over plate separation, is directly proportional to area. Since parallel increases the area, then it says here that the capacitance for a parallel circuit says that the areas add directly. So in other words, this capacitance of parallel is equivalent to adding the areas directly, which then tells us that C parallel is then equivalent to C1, C2, C3. And so this is what we mean by adding capacitors in parallel. And so what you can see here is that just by looking at this, we could see here is that capacitance increases just like area when added in parallel. Because they increase area. Now I can go and talk about capacitors in series. So now I have my same reference as before. So now I have a series, excuse me, I have a reference capacitor, just like we did before. So in this situation, I have a capacitor, and then we'll say that I have, again, talking about my thick plates with my dielectric, I have this capacitor. So what I know about this capacitor is that we don't care about area. What we care about is plate separation. That's all we care about, nothing else. So once again, we are seeing the current coming in here. So now, here's what we know. Adding in series increases plate separation. So how do we see this here? So what I need here is I need a combination of capacitors. So here, I think I'm going to change my color coding to try to make it a little bit more clear. So now I have 3 capacitors. So I'm going to be coming in. And the first thing that I see here is that I see my orange plate right here. Then what I'm going to do here is that I'm going to start to add, I need a different color. How about if I use blue? Okay, so let's make this thicker. So then I'm going to have a blue combination, and then I'm going to have my wire, and then I'm going to keep my blue combination right here, and then I'm going to finish this off right here where I have 3 capacitors that now look like this. So what do I know? Well, this is C1, this is C2, this is C3, and of course we need the dielectric in these capacitors. Now what I'm seeing here is that I have separations. So I'm going to say that the separation between this plate is D1, D2, D3. Now let's look at the charge. What do I know about the charge? Well, the charge combinations should go like this. It should be plus, plus, and then I'm going to have minus, minus, and then I'll have minus, 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 and so I just keep going and plus, add like this. So the first thing that you want to pay attention to is that note that if I look at only the inside plates, that Q net of those inside plates is 0. Because look at that, I have pairs of negative and positive, negative and positive. So they go to 0. So if I look at where the charges are at, I can redraw this combination and I can effectively start to look at this guy and just say, so what are my charges here? So when I look at my charges, I have charges on my upper plate. And of course, I have charges on my minus plate, but there are plates in between, right? I do have plates. So in this case, I'm going to draw these guys without any negative charge because the net charge is 0. But we could say that about anything, any capacitor, right? But this is what I want you to think about. That if this is positive and down here is negative, what you're seeing here is that by adding them in series, I am effectively doing what? I am separating the top and bottom plate with a larger distance. In other words, I can redraw this guy so that it effectively has a model that looks something like this. Where now, here's my orange, here's my blue, and then my dielectric is all right in here. This would be an effective dielectric. This is what we call C series. So if I start to look at this thing, I'm going to say that, again, this is an effective model that works really well with capacitors. So very similar to what we said before, we can now replace 3 capacitors in in series as opposed before. So if I say this again, I'm not sure what I said before, but the reason why we can replace multiple capacitors in series is due to the geometry. And so when I look at the capacitors, what we found here is that we have capacitance, and this time it's inversely proportional to the plate separation. So I can add them. So I could then say, but now this is a bit trickier. And the reason why this is a bit trickier here is because now these guys are inversely. So this tells us that this guy is proportional to 1 over D. So the way we add these then is that that we can replace these guys. So that tells us here, let me be careful here. This tells us here is that capacitors in series add inversely. Because of the geometry of the way the capacitance is. So in other words, if I start to look at an equivalent circuit, what we're saying is that we're saying this, is that if I have 3 capacitors in series, I can replace these 3 with one equivalent capacitance that we call C series, where these guys now add inversely. So that tells us here that then 1 over the series capacitance is equivalent to 1 over D1 plus 1 over D2 plus 1 over D3, which then implies that 1 over series is then equal to 1 over C1, C2, C3. So these guys add inversely, not directly. And once again, it depends on the geometry. So what we're seeing here is that capacitance decreases as more capacitors are added in series.